In this video, we'll look at single loop circuits. In a single loop circuit, there's only one current. All the elements share the same current. What flows into each element must flow out. So if we go around all the elements, it's the same current, and all the elements are in series. In fact, that's the definition of being in series. The definition of being in series is elements share the same current. So in this circuit, we have an EMF device, a battery, in series with resistor 1, in series with resistor 2. We have a current supplied by the battery, which flows through resistor 1, flows through resistor 2, and then comes back to the battery. So that's our definition of series. Elements share the same current. Elements can have the same value current, but but have different currents. For example, in this circuit, both these two resistors share the same potential difference. This battery is wired in parallel across R1 and R2. We could label I1 and I2, where we know from Ohm's law I1 is going to be equal to V over R1 and I2 is going to be equal to V over R2. If R1 is equal to R2, then I1 will equal I2 in value. Their scalar value will be equal, but they're not the same current. The arrows have to be drawn in a different place. So make sure you understand the difference between the same current and a current that has the same scalar value. A single loop circuit consists of only batteries and resistors. If that's the case, then it can be reduced to just one battery and one resistor. And we could use that to find the current in the loop. Or we could use other techniques. We'll show, we'll look at an energy method and Kirchhoff's voltage law to find a current in a single loop circuit. So these are the other two methods we'll investigate, the energy method and the voltage method. We know that this shows here current flowing through a resistor is flowing in the direction of the electric field, so it's flowing from higher potential to lower potential. We know from past videos that our resistor can only absorb energy, that's the thermal energy. There's a decrease in energy, so there's going to be a decrease in electric potential as positive current flows across the resistor. So let's look at the energy method. We'll look at energy transferred is equal to the work done to move the charge. So if we look at our equations here, our power equation for electric circuits is always current times voltage. For a resistor, we can use I squared R. It's good to use I squared R for a single loop circuit since all the elements share the same current. We can look at that differential, that small amount of energy transferred as power times, since energy is equal to the integral of power over time. So we'll look at that differential amount of energy, small amount and a very small amount of time is the power times that small amount of time, plugging in for power. We know that Q is equal to our integral of I dt. So our small amount of charge is equal to the current flowing in that small amount of time. And then we can use our work equation. Work is equal to our Q V, or we use delta V, but that delta V is our EMF here, right? So the change in potential across our battery is delta V, or our E here, or EMF, and that's equal to, and our Q I dt. If we set these two equations equal, we get our differential work. Our EMF times I dt is equal to our differential energy transferred. That's I squared R dt. We can then cancel out the dt's and we end up with our EMF is equal to IR, or I is equal to E over R. In fact, we've just solved for Ohm's law using energy. And that's Ohm's law in this circuit. We'll show that that's because we can take in any single loop circuit that just has EMF devices and resistors, we can reduce it to one EMF device and one resistor. So what we can also use is a voltage method, we'll find is much easier than that. And that's thanks to Gustav Robert Kirchhoff, who worked on Ohm's law by investigating current in resistor networks. And he formulated two very important laws that are principled by the conservation of energy that we just showed, that's Kirchhoff's voltage law, and conservation of charge, and we'll look at that later in later videos as Kirchhoff's current law, also referred to as the junction rule. These are very powerful rules and can be applied to any closed circuit to come up with a system of equations to solve for characteristics or responses within the circuit. Kirchhoff's voltage law, shorthand referred to as KVL, and sometimes referred to as the loop rule because we can use Kirchhoff's voltage law around a loop, so that's one way to use it. And basically the loop rule says that the algebraic sum of changes in potential encountered in a complete traversal of any loop, so if we start at this node A here and come back to node A and traverse it clockwise, we go through a potential increase of V1, and then we go through a potential increase of V2, and then a potential increase of V3, and a potential increase of V4. So the sum of all those potential changes, in this case they're all increases, must be equal to 0. And that's conservation of voltage in a closed system, which follows from conservation of energy in a closed system. The resistance rule that we can use for when we're using our loop rule is that when we move through a resistor in the direction of the current, we're going to have a potential decrease. So we'll call that negative IR. And that negative IR if we're going in the direction of the current. If we're going in the opposite direction of the current, if we are traversing in this direction, well then you can see we're traversing in the direction of potential increase, so we'll call that positive IR. Whenever we're going in the opposite direction of the current, we use positive IR. That's our resistance rule. For our EMF rule, if we move through an ideal EMF device in the direction of the EMF arrow, the change in potential is positive. Otherwise, if we're going in the opposite direction, it's negative. And so we can see if this is our EMF device, if we're traversing it going upward, then we're going in the direction of the EMF arrow, and we've gone in the direction of potential increase. If we're traversing downward here, we're going in the opposite direction of the EMF arrow, we're going in the direction of potential decrease. So if we use these two rules with our loop rule on our single loop circuit, and we start at A and end at A, we see we have an increase of positive, our E there for EMF, and then we have a decrease as we go across the resistor. So we do a negative IR and set that equal to 0. If we work with that, we get I is equal to our EMF divided by R, and again we end up with our Ohm's law. So these two, if we compare these two methods, certainly our energy method is valid and it works from the perspective of energy, and from that energy we can also derive, as we did, this voltage method. To not have to go through the energy method, we can apply the loop rule, the resistance rule, and the EMF rule, and we only need one equation to solve for the current in our circuit. So it's resistors in series with an ideal battery here. Series defines how they're wired together, but we know that means they share the same current. So here they're wired end to end between A and B, these resistors, and the battery then is connected across all these resistors wired in series. Same current through each resistor. The sum of the potential drops across each resistor, so if we call this V1 and we call this V2 and we call this V3, then V1 plus V2 plus V3 must be equal to the EMF of the battery, or the applied potential difference. So if we look at these resistors in series, we apply our loop rule, an increase of EMF, a decrease of IR1, a decrease of IR2, a decrease of IR3. We're back to node A. We have our equation. Set that equal to 0. We pull our EMF to the other side. We pull out the common current, and we can then say our EMF is equal to our I times this REQ, where our REQ is R1 plus R2 plus R3 in this scenario, or in general, it's the sum of all the resistors in series. It's very similar to capacitors in parallel. So resistors combine in series like capacitors combine in parallel. So if we look at this circuit, we know the EMF, we know the resistances, we want to know what is the voltage drop across each resistor. We can label these voltage drops across each resistor and their direction. And then we know using Ohm's law that V1 will equal I times that R1, which in this case is 10 ohms. We can use each of our Ohm's law equations then, and we can do our loop rule, increase EMF minus V1, we're decreasing our potential, minus V2, minus V3, plugging in our Ohm's law, and then pulling out our common current and solving. We get our current is 6 volts divided by the 60 ohms, or 0.1 amps. So we can then plug that back into our equations and solve for V1 is 1 volt, V2 2 volts, V3 3 volts, and then we can do our check that in fact V1 plus V2 plus V3 is equal to the EMF, and we get a check there. We could also look at this circuit, instead of using the loop rule, we could find an equivalent circuit where we see we have 3 resistors in series, so our REQ, our equivalent resistance, looking in between terminals B and A here, is going to be equal to 10 plus 20 plus 30, or our 60 ohms. So this is 60 ohms, and this is 6 volts. And then we can just use Ohm's law. So by Ohm's law here, we have that our voltage across the resistor is going to be equal to 60 times I. We can use Ohm's law, but we know that the voltage across the resistor, since these are equipotential surfaces, these wires represent equipotential surfaces, our VR then must be equal to our EMF. So E is equal to 60I, which implies then that I is equal to E, which is 6 volts. If we let 6 volts, it'll be 6 divided by 60, and we also get the fact that that's going to be equal to our, that should be just 60. I wrote 600. 60, so that's our 0.1 amp, or 100 milliamps. So we can always solve this using equivalent resistances. If we can do that, we can use our Ohm's law, knowing that the potential of the battery is what's across the resistor. Let's look at this more complicated circuit, and we'll do an unconventional counterclockwise loop starting at B and ending at B, and we see we have an increase in potential of E1 in the direction of our defined current I. We have minus I R1, minus I R3, minus I R2. And then we're going the opposite direction of the EMF arrow, so we have minus E2 minus I R4 is equal to 0. So then we can pull our EMF to one side of the equation, and so we have our E1 minus E2, and then we pull our current to the other side of the equation, our current resistance, plus I R2 plus I R3 plus I R4, that's big R. So we have this equation. We can again pull out the current, and we can solve for I is equal to the difference of these EMFs divided by the resistance, after carefully using our loop rule. We can also combine elements in series. We can combine the resistors to have an equivalent resistance. So it doesn't matter what position they're in. If they're next to each other, we can move them around. So we can also move around the EMFs, and we see that we have our E1 pointing upward now, and our E2 pointing upward. We pulled it around here, and our E1 pointing downward, the EMF arrow. But then we can also combine our EMFs, and since we have the positive pointing upward, our EMF arrow pointing up, we end up with an E2 minus E1. And we can then get the same solution for this circuit.